Why does that happen? Because the water expands. In the same distance, you have a solid that turns to a liquid. The liquid expands. Therefore, it's lighter than the rock. And it begins then to do this. So watch this area and this area as we go. All right. And the answer is, okay? See that? And this is where the earthquakes are forming along this side here, California. Forming here, you can see here, in the middle area. These are the volcanoes, these are the volcanic mountains, Mount Rainier, Mount Hood, in western parts of the U.S. This is where they are, this is how they form. Because that rock melts and works its way upward and becomes then Mount St. Helens. That's what it forms. And that whole coast is part of this system, running all the way from Alaska, the Aleutian Islands, all the way southward to Chile and Peru. The entire west coast of North and South America that way. Now let me get back to my normal talk here. Okay. Now, earthquakes have another couple of methods of forming. That one's there where we have this plates are coming together and they have friction, they keep catching. And as they catch them, they keep building up energy. When they stop, then they snap. And they snap is when we have the earthquake form. In another area, we used to have a lot of ice on the continental masses. For example, the nearest ice to here got down to just south of Cincinnati. And let's say 10,000 years ago, there were about 8,000 to 10,000 feet of ice over Cleveland. And about 14,000 years ago, there was approximately 6,000 to 7,000 feet of ice over Cincinnati. Now that's a lot of ice. And ice will weigh about 55, 56 pounds per square foot, or per cubic foot. So if you put 10,000 feet of ice over something, you come up with about 59,000 pounds per square foot of pressure on the rock. And that actually causes the rock to compress. It actually squeezes it down. And as it does, then it holds it down. Then the ice all melted. Most of it melted within a period, about 6,000 years ago, all the ice was gone from most of the continental masses. Okay, so as you see the ice now is about the same as it was 6,000 years ago. And that was like this. Here, sea level rose and fell and this sort of thing. So we had peak glacial periods happening through here. And this is where the ice was at. You see where it's coming down through here. In Europe and so forth, and in the south. Now what that means is it took all the rock that was underneath and it pushed it together. It compressed it. And then when the ice melted, there was nothing to hold it there. But it didn't just go slowly back. Instead, what happens is it jerks. It moves like this. Most of the earthquakes we have north of here, like up around Lexington, you hear once in a while, you hear about, they'll talk about it when the big stadiums have a rattling roof and so forth. Well, these are Richter level 2, 2.2, 2.4, 2.5. And they'll extend all the way up into central Ohio, West Virginia, Pittsburgh, and Pennsylvania. And that's what causes those. Those then are because of rebound, what's called glacial rebound in that system. It's like this at the bottom, here. And that glacial rebound is sufficiently strong that it actually generates a shock wave that gives you a small, minor earthquake. Okay? But most of the earthquakes we have are not basically that. The bigger ones don't come out that way. Those are small ones. This is how some of the major ones happen like this. This would be an example of a situation where we have these rock masses moving together. They're either moving downward or they're moving laterally, sideways, like this. And when that happens, you also have friction along this line here. You start off like this, and in essence what we've got is a situation where this side is moving basically this way. This side is moving this way. And you build up a little bit of tension. You're building up. It's not breaking, it's just bending. Like bending a rubber, especially a rubber band, or bending a stick. Eventually it gets to the point where all of a sudden you begin slipping, and then you have a natural snap, The strain's released, everything snaps back just like a rubber band. And that snapping back is what generates the energy that creates an earthquake. So far, we haven't even got to do that, have we? Okay? Now, what causes the damage in an earthquake? This is the type of thing you have. If you hear news, you talk about people have, okay, they have all these big earthquakes in Iran, and Turkey, and Greece, and all through there. The reason for those are because there are these massive plates are all moving northward. The African plate's moving up north into Europe. India is moving north into Asia. And therefore it's colliding, and that's where you're getting the same stresses here. But in essence, what you're getting is this sort of a thing. Down here, it's moving, sliding, it breaks right in here. And that's at depth. It can be anywhere from a mile down, 10 miles down. We call that the focus. When you're in a newscast, the focus of the earthquake is over da-da-da. The epicenter has been calculated as being in 10 miles south of New York City and so forth. Well, that's what we call here. The focus is here, and as it breaks, it generates a set of waves, energy with pulses, represented by these lines here. Now, if you go straight up from that, vertically upward through the earth, then it'll hit the surface of the earth. And there it generates a second set of waves. And this is what they call the epicenter. So the focus is deep in the earth, epicenter is up here. The waves that are generated here, we are called a P wave and an S wave. A P wave is a compressional wave. The wave does this as it moves. And it's the fastest wave. It moves the fastest. An S wave, or shear wave, is like this. And it goes basically like this, like the waves on the ocean. It's the second fastest wave. But they're all moving through solid materials. The S wave doesn't. It's something liquid, like the molten part of the core, it disappears. And that's somehow we wound up identifying how the layers of the earth were put together. Now when it hits the earth's surface, it generates another set of waves. And these we call surface waves. We call the love wave. The love wave actually takes the surface of the earth and moves it, just like the surface of a lake or the ocean. These are waves. At the same time, we have what we call a Rayleigh wave, and it's doing this. So the surface of the ground, you got waves doing this, and behind it, you got waves doing this. This is the type of motion that creates the damage when we get into the earthquake territories problem we have. And this is what we have. We've begun measuring these by using what we call a seismometer, seismograph. And in these, what we do is we set up a situation where we have a very strong, a very solid pedestal, usually a large mass of concrete, set into bedrock. And then we attach to that, we have a spring, a weight, and a pin, and that goes on a rotating drum. Now when the earthquake hits, what do you think moves? Pin? Correct, it's not the pin. This is what's moving. The pin is staying by itself. The spring isolates it. So what you're actually measuring is a function of the movement of the earth itself. And it makes lines like these. In this case, we have a 1,000-mile earthquake, 1,000 miles from Denver, Colorado, being measured in Denver. So this is what happens. The P wave arrives. Then the S wave arrives. And then those surface waves, the L waves, and Rayleigh waves arrive. And this is one of the methods we can identify where an earthquake occurs, because we know what the speeds of these things are. And when they arrive, it gives us speed, another speed, and the separation here helps give us a control on the velocity that's taking place. But using that, we can identify how far away from a given receptor, a seismograph, an earthquake took place. And this is what we would have in this. In this case, then we can measure it. Here's something called Richter scale. This is the most commonly used method. It's an open-ended scale. If you ever hear someone say 12, a Richter scale 12, you're dead. You're not going to hear it. Because that's the equivalent of a San Andreas fault system that went entirely around the Earth. And this is basically what we have. Richter scale 1 is about 30 pounds of TNT. In other words, somebody taking out a really big tree or moving a boulder. It goes on down. When you get to Richter level 3, that's just about twice to 3 times the size of the bomb that went off at Nagasaki and Hiroshima. It was in about 10 kilotons is what they were, 10,000 tons of TNT. And that's what this is. about 10,000 tons. We're in this area here. So 4 would be about the Hiroshima bomb, Nagasaki bomb. From that point on, number 6 is 1 million tons of TNT, equivalent of energy released.